The energy level diagrams of hydrogen and helium are pretty simple. But when we get into the second row of the periodic table, especially into the p block, the diagrams can get more complicated in a hurry. So let's explore this with a set of simple molecules, the homonuclear diatomic molecules. Here is an energy level diagram for a homonuclear diatomic molecule from the second row of the periodic table. At first, this looks intimidating, but we've learned enough that we should be able to understand it. At the bottom are the sigma and sigma star MOs that come from the plus and minus combination of 1s. This is identical to what we saw for dihydrogen in the last section. The 2s orbitals should be able to do the same thing, giving a bonding and anti-bonding combination. In this drawing, the energy gap between sigma and sigma star is the same for both 1s and 2s. That's probably inaccurate. Since 2s orbitals are bigger, they ought to have better spatial overlap and thus a stronger interaction. So we might expect the energy gap for 2s to be bigger than for 1s. That detail won't affect our determination of bond orders, though. We said earlier in the module that mixing the p orbitals that lie along the internuclear axis lead to sigma bonding and anti-bonding combinations. Again, the bonding MO is at lower energy than the 2p atomic orbitals, while the anti-bonding MO is at higher energy. The other two sets of p orbitals can participate in pi interactions, 2 of them bonding and 2 of them anti-bonding. In general, pi interactions are not as strong as sigma interactions, so the energy gap between pi and pi star is usually smaller than the energy gap between sigma and sigma star. As with atoms, when we put electrons into the diagram, they fill up the lowest possible orbitals. So, up in the 2p portion of the diagram, the sigma bonding orbital will fill before the pi bonding orbitals. There are examples of diatomic molecules where that order is reversed, due to the sigma interaction between 2s and 2p. This is a detail we'll save for more advanced courses. And for computing bond orders, it will not affect our results. Let's do a couple of examples. For the homonuclear diatomic molecules from the second row elements, we'll always use the same energy level diagram. You will not be responsible for constructing the energy levels. The diagram will be given, but you will need to add the electrons and determine the bond order. First, let's determine the bond order for dilithium. We see from the periodic table that lithium is element number 3. That means each lithium atom contributes 3 electrons, and there are 6 electrons in the molecule. While it would not be wrong to add 3 electrons to each side, we really don't need to do that. So let's erase them and only add the 6 electrons to the molecular orbitals in the middle. As always, they go in the lowest energy levels first, 2 electrons per orbital. Next, we need to find out how many bonding pairs there are. We see 2 sigma bonding orbitals that each contain a pair of electrons. There is 1 pair of electrons in an anti-bonding orbital. Using the formula, we find that the bond order is 1. We predict a single bond in the molecule. Our next example uses the same energy level diagram, but asks what is the bond order for the dioxygen 1+ cation. Oxygen is element number 8, so an oxygen atom has 8 electrons. Be careful. We're used to thinking about oxygen having 6 valence electrons, but notice our diagram starts all the way down at 1s, so we need to include those electrons too. 2 oxygen atoms would bring 16 electrons, but the 1+ charge means that 1 has been removed, so this chemical species has 15 electrons. So we drop 15 electrons into the diagram. By the way, when we fill up the pi bonding and anti-bonding orbitals, we would observe Hund's rule just like we did for atoms. For example, if we had 16 electrons instead of 15, the 16th would go into the other pi antibonding orbital with its spin up. For bond order purposes, though, they would count as a pair of antibonding electrons. For the current example, we can find 5 bonding pairs, 3 sigma pairs and 2 pi pairs. There are a total of 5 antibonding electrons which constitute 2.5 pairs. The single electron in the pi star orbital counts as half a pair. Plugging these numbers into the formula for bond order gives 5 minus 2.5, which equals a bond order of 2.5.